We'll be getting started here in a second. Still people coming in. I sent you all, I shared with you Google files that have the collision lab in it. So if you could start whiteboarding the graphical and mathematical models. Something you could do while you're waiting, probably. Okay, I think I'm going to go ahead and get started because I think most people are coming. All right, or here, I mean, already. So let me share with you my screen. Okay, so you did the collision lab, and we're going to talk about that in a second. And what we're going to do today, basically, I know we had another worksheet we're working on, problem number 9, but I looked at some of those, problem number 9 on that worksheet. We still have the whiteboard. I looked at some of those questions, and they use those new words of like elastic and stuff. And I think it makes more sense to actually whiteboard this lab. That way you can talk about those new words and get some definitions before we whiteboard that worksheet. So that probably won't happen until on Tuesday that we'll finish whiteboarding that problem number 9. Okay, so just to remind you what the lab that you were doing was this, and I've got it pulled up. And so you were supposed to do at least 6 collisions, and 2 of them were going to be elastic, and so I kind of want to show you an elastic collision. Okay, it didn't have to be that though. It could be that you had them moving towards one another, and it could be elastic. You could change the mass of them, and you can change the speed of them. Let's say this one's moving this way, and this is going faster, and you could have it be elastic. So you just need to have at least 2 of the elastic collisions. You had to do at least 2 of the inelastic. The inelastic is anywhere in between, but not at the extremes. So the inelastic, so you can have them go in the same direction, like that. You could have them going in opposite directions. You could have it, maybe this one's not even moving at all, and inelastic. So lots of different things you could do. And you had to do at least 2 that were perfectly inelastic. So I'll do a couple of those. There's one. Reset. Maybe they're moving in the same or opposite directions, perfectly inelastic. Reset. Or maybe this one's not moving at all, perfectly inelastic. Something like that. I don't know. So you had to do at least 2 of each of those different ones. Okay. And so what you're doing in this lab was you're looking at the total initial momentum before the collision. So down here, I'm going to hit play for a second and then stop it. But you can see what the initial momentum of the red ball was and the initial momentum of the green ball. Oh, it was moving. I wanted it to be 0, let's say. Let's try again. And so you could add those 2 numbers together to get the total initial momentum. And then after they collide, again, it gives you both of those final momentas, and you can add those together to figure out the total final momentum. And what you're doing is you're going to be plotting those two momentum. I think it kind of makes sense since you're controlling the initial momentum, that the initial momentum would be the independent data, and the final momentum would be the dependent, so it'd be on the vertical axis. Okay. So how about I give you a couple minutes to whiteboard. Let me stop sharing here if I can. Stop sharing. Let me give you a couple minutes to get your breakout rooms and actually whiteboard your lab findings. So hold on a second here. Okay, so let me open them up for you. If you don't get an invitation, you should be able to go down in the bottom, go to breakout rooms, and put yourself in the breakout room. Find your partners, get together with them. So you're just doing the graphical and mathematical models. That's it. So you should have an invitation. So there's a lot of people still here. You should have an invitation. Go in the breakout room, click on that. If you don't have an invitation, go at the bottom and actually choose your breakout room. I'm going to give you about 30 seconds to get in there. If you're not in there, I'm going to assume that you're not really here since I can't see your face. You don't have the camera turned on. I'm going to kick you out. You can't join, can't be in it again, and you will have to watch the video. Okay, lots of people are still here. I'm going to be kicking you out soon. Brandon, there should be a little link at the bottom. You can click out breakout room, put yourself in the breakout room. You are in room 2. John, you are in... looks like your partner's left. Annie, you are in room... Oh, wait a second. Okay. John, 8. John, you're in room 8. Annie, you are in room... Where are you at here? There you go.
Yeah, it just kicked me out when it was trying to send me to the breakout room.
Okay, so Ethan, let me see if I can put you back in. Actually, Ethan, go down to the bottom and go into the breakout rooms. You should be able to put yourself in
Okay, I can see
room
that.
8. Room 8, okay?
Hello.
So Luke.
Yeah.
Okay. You should be in room 7. So go at the very bottom, put yourself, hit breakout room, go in room 7. Okay. Brandon, you are in room, let's see, where are you at here? See if I can send you there. You are in room 2. So if you don't get an invitation, go down and hit breakout rooms, go to room 2.
Okay.
Okay, Annie, you are in room 3. So I'm going to send you to room 3, or try to anyway. And if you don't get an invitation, then click on the breakout rooms at the bottom, click room 3, put yourself in there. Luke, you are in room 7. So you should get it. There you go. Okay. Hey. Hey. Kicked you out.
Mr. Lunfesty?
Yeah.
Luke,
Did you get kicked out?
no, Luke, like, he couldn't join.
Yeah, I think he's in there now.
Oh, he is?
I think so. So can you go back in the room 7? So at the bottom, go to breakout rooms, go into 7.
Okay. Thank you.
Yep. There you go. Okay. Okay, so what we're going to do is kind of look at all the whiteboards, the graphical and mathematical models. So I went ahead and just opened up, and we're just going to we're almost doing it and kind of like in class where we go around and look at each one. So we're trying to find out what the consensus is. So let me kind of, I have to share with you, of course, you can't see. Duh. Okay, so you know what? I don't know who's this. This is Henry's. So it looks like the final momentum is directly related to the initial momentum. By the way, I've shared with you these files so that you can just kind of be completing your lab as we do it. And then as soon as you're done with it, you don't have to share this with me. That's your lab. Now, if you feel like somebody's not pulling their own weight or you totally disagree with somebody, because we're not going to get through all the answers today, you're welcome to make your own and send that to me. But or you're welcome to communicate with me that somebody's just not doing something, so I'll have them do their own. You know, that's fine. I don't have a problem with that, and I won't rat you out or anything. But I need you to kind of do like what Henry and Jaden did here. Is you have to label the axes and put the units in. So the only problem here is I don't think it's kilograms times newtons per second. I think it's kilograms times meters per second, because it's mass times velocity, right? Same thing for the initial momentum. So I'll leave them to fix that. And then please put the title up here. Please put point protectors, although you can make these transparent if you want to. And then also please put the slope indicators. Oh, nice little plus sign. I wasn't even thinking of that. I was thinking like X, kind of like that. But yours are cool too. I like those. And then please put your mathematical model, okay? So just make sure you do that, and notice how they put the final, they put the dependent variable, independent variable, the purpose, all that stuff. So make sure that's all in there. Okay, so let me go around to all the other whiteboards. I don't know whose group this is, so they're still working on it, or maybe they didn't come. This is Malia's and Emily's, I think. Yes, okay. So they also have a direct relationship. This group's still working on it. Who's this? Oh, I can't see. Dang it. Ah, this is Luke and Kyler's. Okay, so they also had a direct relationship. This group here is still working on it. This group here had also a direct relationship. Looks like a direct relationship there. Again, put point protectors, slope indicators, right? Looks like they have a direct relationship. Looks like they have a direct relationship. Don't forget slope indicators, little plus signs or X's or something. Looks like they have a direct relationship. Don't forget point protectors, little circles. And it looks like they also have a direct relationship. So again, don't forget slope indicators. All right. So let me click those off. That means that it looks like, oops, can I move this? It looks like we have consensus here then. The consensus is the mathematical relationship is the final momentum is equal to the initial momentum. I think we all kind of agreed on that. So down here where it says joint consensus model, that is the joint consensus model. Final momentum is equal to the initial momentum of the system. Okay, so let me get rid of those. Okay. Okay, the next part of this we're actually kind of doing together, and that's 17 through 19, because those were those new words that we had to talk about. Let me go back to the lab. So what we just found in this lab is that the final momentum is equal to initial momentum. But think about the lab before this. We found out that there were impulses cause changes in momentum. Clearly, if you look at the red object here, and let me go back to elastic because it's more interesting. Clearly, if you look at the red object, there is a change in momentum because it changed directions, right? It changed speed and everything. So clearly there was an impulse on the red object. So any one particular object has a change in momentum, but we're saying based on this lab that the total initial momentum doesn't ever change. It's the same as the final momentum. So here's my question to you. Notice the red object has a change of momentum. But what about the green object? It definitely has a change of momentum too, right? So my question is this. How does, let me rewind this again. How does the change of momentum, the impulse on the red, compare to the impulse on the green? So you have to unmute yourself. How does the impulse on the red compare to the impulse on the green?
Same.
Almost the same, equal and opposite. So same magnitude, but opposite direction. And that kind of leads us into this first question then. So clearly the momentum of any one car does change. So the red car definitely had a change of momentum. How do the impulses of each car compare? Well, we just kind of answered that. Ethan says they're the same magnitude, but we need to add on to that, they're in opposite directions. So that's the answer. Okay, now going back to the simulation. So we're going to talk about, I think it's, was it elastic or, yeah. No, this is perfectly inelastic. Okay, so we're doing perfectly inelastic. I want you to watch a perfectly inelastic collision and you're going to notice something. Okay, let me rewind. They could even be going in opposite directions. Play. Rewind. This one's kind of a neat one if you could just get it just right. Oh, I didn't get it quite just right. A little bit slower. Almost. Rewind. We can do it even where they're maybe going in the same direction, maybe even. Okay, so you need to unmute yourself. Everybody, please unmute yourself. Everybody unmute yourself. Okay, the question is, what did you notice about the perfectly inelastic collision?
They have the same final velocity.
There you go. They're stuck together, right? So same final velocity sounds very physics. I like that, very physics. But I want you to have a picture in your head. Basically, it's almost like there's Velcro and they're stuck together. So I'm good with same final velocity. That's very important. But the picture I want you to have in your head is they're stuck together. So after the collision, they're stuck together. So let me go back to that question. So how do their velocities compare? They are the same, as Adam told us. And I kind of want you to say, oh, they're the same, kind of like they're stuck together with Velcro. That's the defining characteristic of perfectly inelastic collisions. So that's the definition. They have the same final velocity, they're stuck together. Okay. Okay, now let's look at elastic. This one's a harder one, so let me rewind this. So here is, let me change this to 0. Here's one possibility for elastic. Here's another possibility for elastic. Here's another possibility for elastic. Okay, so this one's a harder one. So what do you notice in this case every time they collide?
They go in opposite direction.
Okay, so they bounce, right? They don't get stuck together. That's one important thing. They're kind of going, they don't always have to go in opposite direction. I don't think, do they? Let's see, let me think here. Oh, this one's hard to do. This one's hard to do. I'm not sure if I can do it. I'll try. Oh, shoot. Nope, I didn't get it. Huh. All right, let's see. Maybe I need to go a little bit faster. Let's see. Rewind. Let me try this. Oh, I know. This will work. This will work. I'll get it right this time. Play. Oh, almost. Reset. Okay, maybe this has got to be slower, and this has got to be faster. There. So, did you see they're going the same direction? So
Yeah.
they don't always have to go in opposite directions, but for sure they're not stuck together. They kind of bounce. So they kind of bounce. So they're not stuck together, but there's something a little bit more important here. So again, can you guys mute yourself again real quick? So let me rewind this. So what's important, there's two things. First of all, they're not stuck together, but there's something more important. Can you look up here, watch the kinetic energy. I want you to watch the kinetic energy. This is before the collision. It's about 4.46. I'm going to hit play. After the collision, it's still 4.46. Let me do a different one. So let's have this one going this way. Before the collision is 2.95. After the collision is 2.95. Okay, the last one, I'm going to have this be 0. Play. Again, it was 2. I didn't say. Before the collision is 2.82. After collision, it's 2.82. So not only do they bounce, but the most important thing is the kinetic energy doesn't change. Kinetic energy it's conserved. So usually we think of total energy is conserved, and it is. Total energy, no matter what, even for the ones where they're stuck together, total energy is conserved. It's just turned into dissipative energy. Some of it is. But if it's elastic energy, kinetic energy is conserved. So the amount of kinetic energy, 1/2 mv squared, is conserved. So let me go back to that question. That's the defining characteristic for number 19 here. That's the defining characteristic of elastic collisions. Is, yeah, they bounce off one another a little bit, but more importantly is the final kinetic energy is equal to the initial kinetic energy. Now, I made a mistake there. Well, I didn't really make a mistake on number 9. Well, sort of. I sort of made a mistake in my question. I said, how does the final energy compare to the initial? Well, the truth is, no matter what kind of collision, the final energy is the same as initial. It's just some of it's dissipative. That really should have been EKF. How does that compare to EKI? And it would be the same. Okay, so everybody got that? Okay, so now we're going to move on to the questions, the calculation questions. Okay, 20 through 21. We're only going to be doing 20 here. Please don't do 21 yet. So let me kind of draw a picture here. So first of all, you're going to be using the relationship we just found, that momentum, PF, is equal to PI. By the way, I'm hoping that you kind of think about conservation of energy, because this is kind of like conservation energy, except it's conservation momentum. And the difference is conservation energy is a little easier because you don't ever have to worry about direction. Conservation momentum, these are vector quantities and we have to worry about direction. So you have to be careful about that. It's also important for these, especially for these, is to draw a picture because of the vector notation. So I'm going to sketch a picture here of these train cars colliding. So here's a red one. We're going to say the red one's moving. Let's say it's moving to the right, let's say. And it's going to collide. Let's say we're going to have it collide with a red one. And that red one is at rest, it says. So it's not moving. So you need to understand that this is the before picture, right before the collision. I also have to draw an after picture. So if you read through this, it says, what is the final velocity of the two-car system, assuming the collision is perfectly inelastic? So if it's perfectly inelastic, what will it look like after the collision? You have to unmute.
Elastic?
Yeah, it's perfectly inelastic. So how will it look after the collision? How will these cars look?
The two cars will move at the same speed.
Yeah, that's right. They're stuck together, moving at the same speed. So I'm going to see if I can kind of draw this. This will be the after picture where they're moving together. And I don't know how fast they're going. They might be going faster or slower. Well, I do, but I'm lying. I usually do that to you guys. You can probably guess whether they're going faster or slower. And I'm going to call this the after picture. This is after the collision. So sometimes students are always like, what's this before and after? Before and after what? Well, we're talking about, in physics, we usually say the event. Usually the event is a collision. So I want you to understand this equation goes with this picture, except it's I here and F on the other side. So the PI goes on this side. The equals is kind of like the collision event, and the PF goes on this side over here, the after. There's two things that have PI. Well, the truth is the red one's not moving, so the initial momentum of that one is 0. But afterwards, we have two things that have final momentum. So you would have to do MVF plus MVF to figure it out. So I'm going to open up. I'm going to stop sharing. I'm going to open up the whiteboards. I want you to whiteboard that problem. Okay, so let me go ahead and open up rooms. You should get an invitation. If you don't get an invitation, go at the bottom where it says breakout rooms and go into your breakout room. Luke, you should be in room 9. There you go. All right. Does somebody want to share their whiteboard?
I can do it.
Okay, yep, at the bottom, just hit share and look what you got.
All right.
Okay, then tell us how, we're just looking at 20, so tell us how you got that, or
So-
walk us through it.
What I did for the first part was I found the initial momentum of each of the objects.
Okay,
So the train car, the only one that was moving and had like an initial momentum was the first one, and that was going to be 4,200.
okay,
Then I added the masses together, 1,200 plus 700, and then times v, and then that was going to be the total momentum, which was still just going to be 4,200. And then I just solved for v, 2.21 meters per second.
nice. Don't unshare, so keep it on here for a second because I want to ask you a question, or maybe the classic question. So everything's perfect, so everybody give Malia a hand. Again, don't unshare though, Malia. So the thing I have is that I actually made a mistake because momentum really is a vector quantity, and so I should have said something like 3.5 meters per second to the north, or 3.5 meters per second to the right, or something like that. So I'm hoping that you understand that then the final answer would be something like 2.21 meters per second. If the initial direction was north, then this would also still be to north. Or if it's 3.5 meters per second to the right, this would be 2.21 meters per second to the right. So if you can give me a thumbs up so I know that you get that I made a mistake there and that I should have had a direction. Okay. All right. Okay. All right. So again, give Malia a hand there. Thank you. Yay. All right. So I'm going to, if you could stop sharing then, Malia. Perfect. And I'd like you to go in and do the next problem. I think that's 21. So let me open up the breakout rooms again. And again, if you don't get an invitation, please go at the bottom, go in the breakout rooms and go into your breakout room. Okay, I know I didn't give you a lot of time on that one, but I think that one was a little bit easier. Can somebody share their screen for that one? Willing to share the problem. Different person, hopefully. Okay, Krishna, thank you very much. Okay, so just kind of walk us through how you're solving it here.
Okay, so it said it gave us the mass and the velocities of the first ball, so we just multiplied that and then we added it times this mass and velocity of the second ball.
Perfect.
And then we did the entire like mass because it's complete system.
Okay, so I have a question though, because the way you have on the right-hand side, you got 0.47 times VF. So do they have the same final velocity, those two balls, afterwards?
Yes.
Okay, so it says, let's see, it says initially they're at rest, but if the final velocity of the first ball, so after the collision, the final velocity is 0, it wants to know what the final velocity of the second ball is.
Oh,
So I don't think they do have the same final velocity. So I think that should be 0.235 times VF plus 0.235 times 0. So
okay.
Krishna, the way you have it right now, though, when you had 0.47, what kind of collision would that have been?
Perfectly inelastic.
Right, right. So this one, they're not stuck together, though. So that's going to be 0.235 times VF. And then plus 0.235 times 0. And I think if you look at it closely, it's kind of an easy math problem. So what's the VF going to be then?
Maybe 4.5.
Yeah, 4.5.
Okay.
So I have another question then for you. So in this case, what kind of collision would this be?
Inelastic.
Well, inelastic would be if there's a there would be some loss of energy, right? But I want you to look at this. They have the exact same masses, and the speed of the first ball is 4.5, and then after the collision, the speed of the second ball is also 4.5. So did it lose any kinetic energy? The speed didn't change.
No.
No. So this is actually what kind of collision?
Elastic.
Yeah, this is an elastic collision. So, okay, give Christian a hand there. Yay, hey, at the bottom, yay, everybody. So in fact, this kind of reminds me, I want to talk about some stuff. So you can stop sharing. I think there's a red button. And I want to share my screen with you guys. I want to go back. And we talked about elastic collision. Here's an elastic collision. I want you to watch the energy, 2.82. After the collision, still 2.82. Elastic collisions are actually a little bit tougher than the other type of collisions because there's two things that are being conserved: momentum and kinetic energy. So the reason why they're tougher is usually when you're doing the math, you're going to have a system of two equations, usually harder. So we also talked about, here's a perfectly inelastic collision. Notice the energy drops quite a bit and they're stuck together. So let me rewind. So what would be, how would you define what just an inelastic? So we're not talking perfectly inelastic. What's just an inelastic collision? How would you define what that is? Anybody? Maybe I'll play it. So you watch. How would you define it?
The kinetic energy changes.
Yeah, watch the kinetic energy. It drops. If you're like, why does it drop? Well, it's because some of it went into dissipative energy. But there's one more thing. Do you notice how they still kind of bounce? They're not stuck together.
Yeah.
So perfectly inelastic, I'm going to rewind it. Perfectly inelastic, the energy drops, but they're stuck together. Just inelastic, again, the energy drops, but they're not stuck together. They're not stuck together. Okay?
Okay.
All right, so let me minimize that again. All right, so now we are going to whiteboard. What's the next one? 22. So 22, don't worry. Hey, please don't start on 23 through 24 because those are really tough ones and you'll probably make a mistake. Can you please just do number 22 now? Let me go ahead and open up the whiteboard room. Okay, whoops, I made a mistake. Sorry about that. There you go. Should get an invitation. If you don't get one, go at the bottom, go to breakout rooms and go into your breakout room. 22.
Mr. Lefus, yeah, I can share my screen if you want.
Oh, awesome. Let's wait until everybody gets here, but I'd appreciate that. Yeah, that'd be awesome. Okay, and Adam said he's going to share his screen. So yeah, Adam, go ahead and do that. Okay, and just kind of walk us through how you got your answer there at 4.55.
So I did the kilograms or the mass of the semi-trailer times the 5 meters per second, the velocity, and then I added it to the initial velocity of the bug, or what the Volkswagen bug, and which was 0, so it cancels out there, and then you just get 50,000. And then since that's the initial, it's also the final because it's inelastic. And then so you put that back in and you set it equal to the total mass times the velocity, and then the velocity is 4.55.
Okay, so again, don't unshare because I want to talk about some stuff. So again, I hope everybody understands I made a mistake on this. I really should have made sure it was vector. I should have said something like 5 meters per second to the northeast. That means then the final answer would have been 4.55 meters per second to the northeast. A couple other things, Adam, I heard you say that it's conserved because it's a certain type of collision. What kind of collision is this again where they're stuck together?
Sorry, what did you say? I couldn't.
I'm sorry. Yeah, what kind of collision is this where they're stuck together?
Isn't it inelastic?
It's called perfectly inelastic.
Oh yeah, sorry.
Perfectly. So actually, I also want to make sure that people understand that momentum is always conserved, whether it's elastic collision, perfectly inelastic collision, or just inelastic collision. It's always conserved, assuming there's no outside forces like friction or air resistance or anything. It's always conserved. So could everybody give Adam a hand down there? Yay. Awesome. Okay, you could stop sharing. That works. All right, so I don't really want to spend more time solving the next one. You're gonna have to do as homework, but I want to kind of give you some pointers because it's kind of a hard one. So first of all, you got to kind of draw a picture. So let me pull my picture up here so we can see it better. Move this up a little bit. So we have two skaters, one on the right. So the girl over here, she has a mass of 70 kilograms. And the one over here on the left, she has a mass of 48 kilograms. The skater on the right is tossing this medicine ball, this 15 kilogram medicine ball, towards the skater on the left. And the skater on the left is going to catch it, okay? This medicine ball is leaving the person on the right at a speed of 5 meters per second. Okay, so here's the tricky thing about this problem, is that you can't do this all at once. You can't make your system like this. This will not work, okay? You cannot make your system like that. It won't work. You have to do it as two separate problems. That's why I'm listing it as 23 and 24. So for the first problem, you're just looking at the girl on the right, and she's holding the ball. She hasn't thrown it yet. The event, this isn't a collision. The event is her holding the ball. So I should say her throwing the ball. So as she's just holding it there, so I'm hoping you're imagining this. She's just holding it. She hasn't thrown it yet. She's just holding it. What is the total initial momentum before it's thrown? Everybody has to unmute yourself. Please tell me, what's the total initial momentum?
0.
It's 0, right, exactly. And so when you do PI equals PF, the initial momentum is 0. The final momentum, it's going to look like this. This girl on the right is going to start moving to the right. So she's going to be moving like this, away. And the ball is going to be moving to the left. So when you're doing final momentum, you need to realize they're moving in opposite directions. So one of these two has to be negative, either the girl or the ball. Something's got to be negative. And they give you the velocity of the ball, or the speed of the ball is 5. So either that's a positive 5 or a negative 5. You need to decide. It doesn't matter. So when we're talking about number 23, and again, we're just talking about the girl on the right and the ball, do you guys think you understand what you're doing there? Or give me a thumbs up if you're getting that. Yeah, okay, all right. Now for the second part of this problem, the girl on the left is going to catch it. So now we're getting ready to do number 24. Okay. So this is the system now for number 24. It's just the ball and the girl. Okay. On the left. Initially, the ball is moving. Okay. So you have to totally forget about the other part of the problem. When you're like, wait a second, I thought initially she's just holding it. Well, that's for 23. For 24, we don't care about the girl on the right anymore. We only care about the girl on the left. So for number 24, the ball is moving. It's moving toward her. So initially, it has momentum. How much momentum does the girl have initially? You have to unmute yourself. How much momentum has? Zero. Good. Afterwards, this is a tricky thing. This is where students make a mistake. Afterwards, she catches it. She doesn't drop it. She catches it. What kind of collision is that where she catches it?
Perfectly inelastic.
That's right. Perfectly inelastic. That means the ball and the girl, they're going to be moving together now to the left. Okay. And they're stuck together. So any questions about number 24?
So,
No. Okay. Okay. So maybe give me a thumbs up. Actually, wait a second. How about give me a hand, or like a raise your hand if you have a question. Can you? I'm going to stop sharing. Raise your hand if you have a question. Okay. So let me share again. So let me go back to the calendar. So your homework then for tonight is to finish that lab response. And again, I made folders for you so you can just answer it right there. I imagine that a lot of you are pretty close to being done already. And I'd like to get that by midnight. Okay. So, and again, if somebody's not contributing, maybe let me know and you just turn in your own. They can turn in their own or something. Okay. There's also quiz, and I want to show you the access code for the quiz. It's just 5 questions. These questions are just over the lab, like what was the relationship and what does elastic collision mean and that kind of stuff. The code is 409-276-482. 409-276-482. 409-276-482. So let me stop sharing. You know how I always take a picture at the end for attendance? I'm going to do that again, but I want to change it a little bit. So go ahead and turn on your cameras. I'm going to change things a little bit. I've been doing this last couple of days. It's kind of fun. I think it's fun anyway. So most of us have pets. Could you go retrieve your pet, either cat, dog, hamster, hedgehog, fish? If you don't have a pet, maybe you have a stuffed animal that you like to cuddle up with, or a blanket or something. Could you go get it? And I'd like you to pose it right in front so I can get you and your pet picture. Oh, that's a nice cat. We got a cat there. I got a cat too. My cat's hiding. Oh, there's a pet. Malia, what is that? I can't hear you. Can you unmute yourself? What? It looks like it has arms.
It's a virtual background of a bulldog with
Oh,
wrinkles on
okay.
it.
Okay. Okay. So, oh, there's a dog. Nice. Oh, there's a painting. Okay. Oh, that's all right. Okay, cool. John has a beach ball. That's his pet. I like that. Okay. So, all right. We all ready? Okay. So,
I don't have any.
you don't have a favorite thing that gives you comfort? Luke's got a car. He likes to play with the car.
I got a goat.
A goat. Okay.
I got a
All right.
goat.
Okay.
Over here.
Okay, count of 3. I'm gonna get your pick. Oh, there's a nice dog there. All right, ready? 1, 2, 3. Okay. Nice. Thank you. That's perfect. That was awesome. Okay. So the next time we get together is on Tuesday. So that's it. See you guys later. Have a nice weekend. Bye.
Thank you. You too.
Wait, Mr. Lundqvist?
Oh, yeah. Question.
Do we have to do the lab? I mean, the attendance book if we already presented or
Yeah,
not?
I want everybody to do it. So here's the reason why. There's no mathematical questions. It's questions about the lab. Like, what was the relationship? What's elastic mean? What's perfectly inelastic? Because that stuff's kind of important, and I need to know that you understand those concepts. It's not really hard stuff. It's not math. It really shouldn't take more than 5 minutes.
Can you reshare the code?
Oh, sure. And there's the picture, sorry. let's see, the code is 409-276-482.
482. Okay, thank you.
Yep.
Okay, see you, Mr. Lundfest.
See ya. Bye. Shouldn't take very long to do that. Oops, what am I messing up here? I don't know what the heck I'm doing wrong.